Okay, so this should have been in the last video, so I hope you're watching this immediately after the last one. This fact that these two notions of rank are actually the same, the rank of a linear map and the rank of the matrix that represents the linear map, those two are always equal, that has some nice consequences. It lets us observe some properties of linear maps just in terms of the matrix of those linear maps. So, for example, suppose we have a linear map represented by an m by n matrix H relative to some bases for the domain and codomain. So in this situation, if H is represented by an m by n matrix, that means the dimension of the domain space V has to be n, and the dimension of the range space W has to be m, right? So it turns out that H is 1 to 1 if and only if the rank of its matrix is n. And this is a consequence of the fact that the rank of H and the rank of the matrix H and the rank of the linear map H are the same, because we've proved before, when we first talked about rank and linear maps, that a linear map H is 1 to 1 if and only if the rank of the linear map is equal to the dimension of the domain space, right? Because this actually came from the rank nullity theorem, because if the rank of H is equal to the dimension of the domain space, then this is another way of saying that the nullity of H is 0, and we've seen that if the nullity of H is 0, then H is 1 to 1. But if the rank of H is n, well, the rank of H is n if and only if the rank of its matrix is n. Right? So you can tell if a linear map is 1 to 1 by looking at its matrix and seeing what the rank of the matrix is. And that's much easier because we know a lot more about matrices, right? How do you find the rank of a matrix? Well, you just row reduce it and count up the pivots. How do you check if a matrix is 1 to 1? Well, that's a lot more work, right? Similarly, the linear map H is onto if and only if the rank of the representing matrix is M. And the proof of this is very similar. So H is onto if and only if the rank of H is M, right? Because the rank of H, we define this to be the dimension of the image of H, right? So to be onto, your image has to cover all of W, so the dimension of your image had better be M, right? But now we know that the rank of H is M if and only if the rank of capital H is M. So again, we can check if a linear map is onto by thinking about the rank of the representing matrix. And working with the representing matrix is easier, again, because to find the rank you just row reduce and count up the pivots.